Can folks hear me? The mic working? I think it is. Okay, great. Today we're going to kind of change topics from before. We were talking about conv-nets before, and we're going to switch to talking about graph neural nets. We kind of finished up everything I wanted to say about conv-nets last time. And as you can see, your homework, which was released on Friday, is entirely on this topic. So fortunately, this topic is one where you can actually bring together different things that you understand, different streams of understanding, and hopefully deepen your appreciation not just for the specific topic of graph neural nets, but also understanding deep learning in general by providing a different perspective from a conv-net. Before I get into it, though, I did want to acknowledge that there's like a few really nice resources online that you might want to look at just for yourself. One we link in the homework itself, and so this is a blog post from folks at Google Research. Again, this one it's in the homework. I'm just going to list it up here. And the other is actually a library and a framework that builds on top of PyTorch for deep graph neural nets, which is called, very simply, DGL, Deep Graph Library, .ai. So everything I say is going to be kind of motivated conceptually. I'll talk about a couple of different ways that'll hopefully help you understand what's going on there, too. But at dgl.ai, you'll also find a really nice resource that they've taken. They've basically made a lot of example code available to you, where they've taken different papers, they link the paper's original repo, where they had some self-built implementation of a graph neural net, and they have their version using their library, kind of standardized examples for you to see what's going on. So you might find this library and the examples there helpful to your understanding. There are, of course, a lot of details and implementation details, just as there are for conv-nets, that kind of go significantly beyond what we're going to talk about in lecture. But hopefully, lecture will allow you to read papers and resources online to understand that stuff, that level of understanding. Okay, so it turns out that there's two ways of understanding graph neural nets, and you'll see both of them if you try to read the literature. So two perspectives. The one that we're going to take is we're going to take the perspective of we want to generalize CNNs. Graphs. So where the idea is where in the CNN you had images, you want to go from images to some kind of graph. That's the perspective we're going to take because it's natural, having talked about CNNs before. But I wanted to acknowledge there's an alternative perspective that a lot of the literature and papers, including this blog post, kind of go back and forth between. And that other perspective is generalize graph algorithms to be learnable via neural nets. So if any of you have taken courses in any kind of algorithm or data structure things, graphs are one of the standard topics. And you've thought about algorithms on graphs. In addition, graphs are very natural and come up with all kinds of algorithmic settings. For example, in error correcting codes, there's graphical models in probability, and one does inference on graphical models by message passing. So there's all these different algorithms that exist that have been handcrafted by humans to do a good job in extracting the relevant information from a graph, from graph structured data. And so the alternative perspective on graph neural nets is to say, well, we have all these handcrafted algorithms. Can we get a neural net to also do interesting things and learn such algorithms on its own? Okay, so both perspectives are there. And in the homework, we actually try to remind you of some of the stuff just on graphs to help you connect to what's going on. Okay, so just a little bit of a preamble. So the basic idea that we're going to view it as is basic idea is go from images to graphs. So what do we mean by an image? When we think of an image as being the data comes to us in an image in a very structured way, right? So this is, by an image, we mean structured. There's some height, there's some width, and there's some number of channels, data. And we want to understand that instead, this idea of images, we want to move to a general idea of a graph. So that for a graph, we just have nodes, edges between them, and let's just say both nodes or edges could have their own information associated with like a vector. Some Vn information, some real value, real C for nodes, node n, and similarly, you might have labels for edges too. So basically, it says we're going to replace this thing with, I have like an example that I chose on purpose. This kind of thing. Okay? So lots of information in the real world can be thought of, can be abstractly viewed in terms of having some kind of connectivity information between nodes and information held at every node or on edges. The classic examples are, of course, things like transportation networks, but there's also social networks, people connect to people. You can use graphs to model relationship among products. You can use graphs to model, for example, where a lot of graph neural network really has gotten a lot of oomph, has been actually in thinking about chemistry, where you think of molecules having graphical structures associated with them. So hopefully this is, the big picture here is clear. Any questions on what we're trying to do? Right, so we're trying to see, okay, can we take what we know and apply it away from images to something else? Okay, good. Now, what I want to do is to say, okay, suppose you were, take yourself back in time. I think the paper on graph neural nets, the one that kind of launched the field with its name and so on, I think it was 2009. So go back, to a hypothetical alternate world where it's, 2015, and no one has thought about graph neural nets yet. Okay, and you understand ResNet, you understand convolutional neural nets, and someone asked you, hey, we're a startup, and we've heard all kinds of great things that are happening with using deep learning for images, but we work in the area of chemistry, where our basic objects are these molecules. Hey, can you tell us, make neural nets work for us? Okay, do you understand the idea that you might kind of hypothetically? So how would you begin to approach doing that? Right? How do you invent for yourself the concepts of a graph neural net? So that's what I'm going to try to work with you guys through in this lecture. Kind of how can you think about it instead of having it just be told to you? Okay. So to do that, I'll use this board for a moment. What you're going to do is first you're going to say, hey, for a convnet for images, what are the big ideas? What did we learn for a convnet that we can use? And we're going to see how do we generalize it. And which ones of those will generalize easily, and which ones will generalize in a more difficult way, or won't generalize. Convnet key ideas, ingredients. So let's just list some of them. So one, you definitely have convolutions. So these are local operations. With weight sharing. Across different positions in the image. You have the idea of depth. To increase the kind of receptive field. And allow, quote, distant pixel information to be used. Right? Because you have this idea of a CNN as having depth, right? We have residual connections. From ResNet. Because once you have depth, to prevent dying gradients. We have normalizations. adaptively speed bump exploding gradients. And we have the idea of pooling to downsample. And speed up, growth of the receptive field. And pooling also had this attribute which you saw of routing the gradients, right? Okay, so these are like ideas, right, that you saw in convnets, right, that allowed you to make a convnet. And you had the idea that, okay, on top of all of this, you do this kind of stuff, and then you can stick in, some final multi-layer perceptron, which you can think of as a one-by-one convolution, right? You could stick something in at the end, right? Any questions on these, like these key ingredients? These are hopefully all familiar to everybody at this point. So now the question is, how can we, how do we begin to think about how to adapt all these ideas to graph neural nets? So of course, what's the big picture here? The big picture here is that we want to work on data that has comes to us in a graphical structure. We want to adapt neural net ideas. So we start by adapting the ideas we can, and then we see, of course, how well does it actually work. Okay, like we have to see how well it actually works. So here, I wanted to kind of also point out something that we already have in convnets, but is also turns out to be particularly interesting in the context of graphs. So already in the what kinds of problems? Are we going to try to solve? So you already saw in images that we had, of course, the image level problems. So again, let's think about it this way. CNNs, GNNs. So already in CNNs, you saw how we introduced everything, was you have image level problems, like identify this picture and tell us, is it a cat or a dog or a banana? Things like this. So you have image level problems. Tasks. Could be classification, could be regression. It kind of doesn't matter. But the idea is that there's one output for the entire image. One target for the entire image. So the counterpart in GNNs is the graph level task. So a graph level task would be something like, suppose you have a graph that represents a particular molecule. So it's labeled, all the bonds are there. It's labeled with, what atoms there are and so on. And the graph level task is, so for example, binary classification. Is this poisonous or not? Okay, do you see? Or graph level task could be, at what temperature will this thing melt? It's a regression type problem, right? The one that's in this this blog post, I think, is like, is it smelly, right? So there's lots of you can see lots of things when you use a graph, and you want to kind of say something for that you want to learn something You learn a pattern that basically allows you to go from the graph with its information to something that's true for the entire graph as a holistic whole. Okay? But with CNNs, we saw when we were talking about UNets and things last time, is you also have like pixel level things you could try to do. Right? Which is to, for example, do semantic segmentation, where you take an image and the output should be another image that has every pixel labeled with what type it is. Right? Is it a cow? Is it a person? And so on. So you can also have pixel level tasks here. And the same way, in a graph neural net, you can have tasks that are actually aimed at the node level. Like you want to say something about each node. Everywhere I say nodes, you understand between the duality of nodes and edges. You could imagine the same kind of problem at the edge level. Okay, I'm just not going to write it out separately. So what's an example of like a graph for which you would have a node level task? So it turns out, so just to be clear, you might not hear so much kind of in the popular press about graph neural nets the same way you hear about conv nets. But from a commercial point of view, they're incredibly important because a lot of natural commercial data is naturally graphed. For example, you have nodes for customers and nodes for products, and which person bought which products at what price is your graph of information that you have. And you want to do all kinds of interesting things from there, right? And that's where a lot of node level tasks become quite interesting, which is, for example, you could imagine like discriminative pricing. What price should I charge a person for this product? That's actually edge level, right? Or recommendations. Do I want to recommend a particular product to a particular person? Or how valuable is this customer to keep? And also in security, there's lots of security-related data that comes naturally as graphs. For example, lots of logging information can be viewed graphically. And there's a very important node-level question that occurs in security, which is this person an attacker? Is this node compromised? Is this thing compromised in some way? Okay, so there's lots of such problems that are kind of node level. Now, one thing I'll already acknowledge before we start talking about kind of making the parallels is in CNNs, in the context of CNNs, with small exceptions, almost all of the tasks you hear about and the kind of training data you have, you're given lots and lots of different images to train on. Okay? You have lots of images to train on. For graph neural nets, because of their origin, there's many cases in which the data that you have access to is actually like one graph. It might be a huge graph, but it's like one graph. So for example, if you think about Facebook, Facebook has a social network graph of all the people, and who they're connected to, how they've interacted on Facebook. Right? They have a giant graph like this with, I think more than 1 billion nodes in it. But they don't have a whole set of such examples. They just have that one. Do you see that? Right? So another place where this kind of thing happens is you could imagine, you have the record of all transactions on Ethereum. Right? So again, that's like one thing. Right? You could turn that into a graph. But it's not like you have a whole bunch of training data that is like relevant to this, that's all kinds of other stuff. You see what I'm saying? So this is one thing that's a bit different in GNNs, is that sometimes in GNNs, the data you have is just one graph. And you have to learn the pattern from just that one graph. So it could be, for example, one graph, especially for node level tasks. Of course, that kind of thing applies to node level tasks, not to graph level tasks. Because if you just have one graph, it has one label. But node level, it's still interesting when you have a big graph. So that could be, for example, you have partial labels on some of the nodes, but you don't have labels for others. Okay, hopefully that's clear. Any questions on that kind of topic? So you'll see in the homework, the example we give you, the graph neural net homework problem, the last problem on the homework, is basically there's a single graph and there's a node level task of kind of clustering that you're given. Like figure out what these nodes, or kind of classification. These nodes break up into two groups. What are those? How do you predict that for certain nodes? Where you only have actual data for some of the nodes. Okay? So, coming back to this. How are we going to think about adapting the ideas? For adapting the ideas, we're going to focus actually on a graph level task because that's the most analogous to what we have here, right? Just for thinking. If you want to keep something in mind, just think about it as a graph level task. So for this, whenever you're trying to generalize ideas, you want to start with what you think might be the easiest case, okay, to think about, and then reason out from there. So the easiest case for purposes of thinking is that we're going to try to be exactly like images. So for images, when we thought about images, we thought about building a convnet for a particular size of image, right? So we have an image, we're building a convnet for CFAR10. There's a particular input size, a particular number of channels, 3, that we're going to use. So we want to think about, like, what is the counterpart of that? So the counterpart of that is, the easiest case is, we have a single graph topology. Okay, so like this graph. Okay, and we just have different labelings on it. Data set consists of different labelings. So we have different information present at the different nodes or different edges, and we have different overall labels for the graph, whatever, okay? Do everyone see how that's a simplifying assumption? Because that makes it more like we already know for CNNs. It's almost the same thing over. Now let's see, how do we generalize the idea of a convolution? So want counterpart of convlair. So for making a counterpart of the convlair, we kind of need to see about what do we want? What do we mean by a counterpart of the convlair, right? So if you think about the convlair, it says, look, I'm going to do this local operation on the local neighborhood of every pixel. Especially because you saw originally for example, in ResNets, people kind of zoomed in on 3x3 convolutions as the thing to use, and just you stack them up in depth. So if you think about a 3x3, we'll draw a picture of a 3x3 here. So a 3x3 you can think of in the following way. There's me, there's north, east, south, west. I have my immediately north neighbor, my immediately east neighbor, and so on. And then I have the northeast neighbor, the southeast neighbor, the southwest neighbor, and the northwest neighbor. So if you think about a convnet with 3x3 convolution says, hey, how do I combine information from my different neighbors appropriately to come up with a new value for this channel of this pixel? Okay? Everyone sees that? So we want to have that same thing, right? So we want to respect graph local topology. And in a convnet, what we did was we had weights associated with these, right? So this was turned into a weight matrix, right? W1, W2, W3, W4, W5, W6, 7, 8, and 9. And we had those weights shared, right, across all the different positions in the image. So you want to respect the graph's local topology and share weights, share the learned weights across the graph. And just as we have in a conv layer, we're totally fine with adding more channels. Okay? So the output of the conv layer in a convnet is another image. And it's another image which might have more channels. Right? There's a way of thinking about the output of a conv layer. The same way, we're going to have the output, we want the output of this to be another labeled graph, except we could have more channels. Right? So all those ideas almost generalize, except we have to figure out how can we respect the graph local topology. We can add nonlinearity and all that. Okay? So now here it's actually interesting to distinguish between the two cases where we have edge labels and we do not have edge labels. Many graphs do not have edge labels. And you know from, we might have seen in other classes, if you have a labeled, a graph that has edge labels, you can also just turn that into a larger graph that has only node labels and has edges that are unlabeled, right? Just by adding a node for every edge and stuff. So it's important for us to understand what happens for things we do or do not have edge labels. So start with the basic case first. The basic case in the sense that it makes it most different. Basic interesting case. Case is no edge labels. Okay, so start with the case of no edge labels, because it's a little bit harder. Then we'll understand how to go back to the case with edge labels. So for no edge labels, right, suppose that this is me, counterpart of me, right, the node you're thinking about, this one. All you know is that you have, the local topology just tells you, looking at that me, that you have two neighbors. This thing and this thing. Does everyone see that? Important thing, neighbors in a graph are not a list, they're a set if you don't have edge labels. Does everyone see that? Okay, so challenge, key challenge. Something that's different. Neighbors are a set, not a list. There's no order to them. By contrast, in a ConvNet, you saw how I wrote W1, W2, W3, W4, W5, W6, W7. This is like a list. Because my neighbors are a list. Because I have specific ordering I can put on them. Right? My northwest neighbor is different from my east neighbor. But if you don't have edge labels, the new thing I see is that I don't have a list. I just have a set. Second thing is that you want to think about weight sharing, right? So this me has 2 neighbors. This one also has 2 neighbors. This one has only 1 neighbor. So I'll write that down. 2 neighbors, 2 neighbors, 3 neighbors, 1 neighbor. I'm not counting themselves, right? So another challenge is I can have a different number of neighbors. Can be a different size. For different nodes. Now the question is, how can we have... So what that does is it immediately, for this case, it throws out what you might have thought would be the natural generalization, right? The natural generalization you might have thought is, oh, great, I'll just have W1, W2, W3, W4, W5, just as I had in a ConvNet, and I'll simply take W1 times my first neighbor, W2 times my second neighbor, W3 times my third neighbor, and then have a W 5 for myself, and so on, right? It doesn't work because I don't have a first neighbor. I only have a set of neighbors. Okay? So your first idea would be to say, okay, because I cannot distinguish my different neighbors, I just have to use an identical weight for all of them. Is that clear to everybody? Right? So the first idea must use a single weight, learnable weight, W, for all neighbors. I guess you always know who you are, right? You have yourself and your neighbors. So you can actually use, and possibly a second one, W me for myself. And so you could proceed this way. To say my graph neural net has to use a single W for all neighbors. Now, actually, you do have something that's ordered, right? You have the channels. The channels are ordered. Because the channels are vectors, right? We said there's a vector. So you have the first channel, the second channel, the third channel, the fourth channel, and so on. Do you see that? So you could use a different weight per channel, right? So you could have a learnable weight per channel for others and a learnable weight for yourself per channel. So just by itself using a single weight, of course, you might think this does not have enough expressive power to do something interesting. Right? It feels very, very, very limiting what you can do. All that basically means is you can do some kind of, if all you had was a single weight, not something that was per channel, all you can do is a kind of weighted average of my neighbors, right, with a different weight for myself. And that's it. That's not very much. You can kind of imagine what would happen if you did that on a network and just ran it for many, many layers, because you're going to do that for depth, is you end up just taking a big global average of some kind. You'll see that? So not necessarily as expressive as you want. Being able to do something different for each channel adds a little bit. Then you want to say you can add a nonlinearity, so then maybe you get a little bit of expressiveness. But what it means, though, is for graph neural nets, people usually step back a little bit and say, OK, let's really think about what we need from this operation, and let's allow ourselves to do that, whatever we want to do, what we need to do. So now I'll just talk about these. So for a GNN, without edge labels, we want functions that are given output some function of the data that's here. I'll call that me, okay? It's like whatever's here. And, a set of information from neighbors. Me info, like local info, and set. So a set of vectors. This is a vector. So for something to be a valid function of this, the challenge really comes down to a little bit for implementation. Because you don't have, if you implement a set, inevitably in a computer, a set is implemented as some kind of list or array, right? The implementation always has order, just because memory is arranged linearly. So if you want to respect the graph, though, you need to make sure you don't depend on that order. Okay? So we need permutation invariance. On neighbor information. You're allowed to treat yourself differently because that's part of the graph. You're doing computations here. So there's lots of examples of this, right? And there's examples that break this. But this is for something to be a valid graph neural net operation of this kind, it has to have this permutation invariance if the graph doesn't have edge labels. If the graph has edge labels, your neighbor info is actually now pairs, right? It includes the information from that neighbor and the edge label. But it's still a set. It's a set of pairs, okay? So these kinds of functions are called aggregation functions in the graph neural net community because they aggregate information from neighbors, from local neighborhoods. So let's do some examples of these. So at this point, you realize that if you want to do a graph neural net, you might not want to just stick to linear things, but let's acknowledge linear things. So examples. So all the examples, you can imagine a nonlinearity that you apply to the end, right? So you can think about an example where you have some f nonlinearity that applies to some weight me vector, right? Dot product, I'll use inner product notation, to the me plus a sum of inner products learned weights and vi from the neighbor I, neighbor of me. You can do this. This is like a linear combination of neighbor information that is also combined with itself, then run through some nonlinearity. Okay, so this is the valid example. And of course, you can do a bunch of these, right? You can have different ones of these if you want for different channels. Is that the only example? No, we have more, right? So you can have the same kind of thing, except you could have an average if you want, because you know the size of a set, right? You know the size of a set. So averaging. So summing up things is permutation invariant. Averaging is permutation invariant. Can anyone tell me another operation that I can do on a set of real numbers that's permutation invariant? Yeah. I could multiply them, yes. Multiplying like a product, yeah. So, also can become product. What else? Max. You can just call them out. Max. Anyone else? Norm, yeah. As long as the norm is appropriately symmetric, right? So appropriately symmetric. What else? What else can I do? I guess there's min, which is like max. Right, so all of these are kind of valid operations that you can do. We already have averaging written, right? So average. In the spirit of averaging, right, and maxes and mins, is there a particular kind of operation that you also want to kind of call out, even though it's like, what do you have? What have you learned that's kind of like a max or a min and kind of like an average, but seems to be useful in deep learning contexts? Softmax, right? You can also do softmaxy things. By which I mean you take something like the log of the sum of e to the something, that style, right? With the idea that exponentials are dominated by their largest exponent, and so when you take a sum of them, you just get something just like the largest, and the log will bring it back, right? So this kind of stuff also is valid, right? It doesn't care about the order. So this is like your range of things you can kind of work with. This is one set of examples. But actually, you can do more than that, right? Because you're allowed to have a different thing for myself, me, versus others. So here's another example. So I'm going to write it a little bit more kind of abstractly. So you can have a function that depends on vme in some way, separately, some separate dependence on vme. And then, actually, so if you look at this, it has two parts. It has a part that has to do with me and a part that has to do with neighbors. But actually, we could have an interaction term between me and neighbors. Do you see that? Like, that's legit to have an interaction term. So you could do something, again, I'll write a sum, but it could be any one of these kinds of operations, where I say I'm going to weight the information from my neighbor, not just by something having to do with a learned weight having to do with that neighbor, but actually some similarity function that might have learned weights that has to do with me and the neighbor. There's always some learned weights here also, right? Could be learned. Did everyone see that? That's also natural in the graph context. So in the graph context, that would be saying, look, I want to look at information from my neighbors where the neighbors that are more similar to me are more important than neighbors that are different from me. Of course, it could be, you could modulate that some way, right? But the idea is you could have a function that depends on yourself and them. Any questions on this kind of valid operations that you can have? Okay, good. So with this, you can also see that if I have edge labels, all that does is change the neighbor information to be a set of pairs, a bunch of pairs. And so you can have the set of pairs also be used, right? So you're allowed to actually look. You can imagine not just doing a linear operation here, but looking inside of them. So it's a good exercise for you. I'm going to move this over just for a second. It's a good exercise for you to think about if you had a directed graph. So I talked about undirected graphs first, but everything here I'm talking about also applies to directed graphs. Neighbors are those, you have two sets then, right, of neighbors. You have those who have incoming edges to you, and you have outgoing edges neighbors. So now you have you have two sets, in edges, out edges, that are all relevant information from the graph. So imagine if you took an image and actually represented it as a graph with labeled edges that were always the discrete labels, northwest, north, northeast, west, me, and so on. You see how you can turn an image into a graph with these labels? Where you have one node for every pixel, and you have edges that connect neighbors with labels. Okay? It should be the case that using graph neural net type operations, you can not exactly recover a content. Okay, do you see that? It should be possible to do this because you haven't lost any information. So it's a good exercise for you to think about how you would do that, what kind of operations you would do to do that. And so what I'm trying to say is that you can have basically the learned weights, right, that allow you to combine could depend on the edges, on the edge information, edge labels. So the examples we gave here are just meant to be illustrative, but you have a lot of richness of what can go inside these functions. Okay? And so one should take advantage of it when it's useful. Of course, you still have all the same considerations that you have in neural nets generally. You got to make sure that whatever aggregation operation you pick has decent gradients going to the weights that you're learning. Okay? Yeah?
So in these examples, like these WIs, how are those reused? Are they? It kind of looks like things are all different.
Great question. So we're talking about weight sharing here. The question is about weight sharing. So I'm already talking about it assuming weight sharing. So the function is the same for every given node in the graph at this layer. So the weights are one set of weights that are learned. Same as for a convolution. You learn one set of convolution filter weights, and they're applied for every pixel. So same here, you're going to learn one set of weights for the aggregation operation, and you're going to apply it kind of across the entire graph to get another copy of the graph, except with more channels of stuff.
The WI there, it's that.
There should be no WIs anywhere. Yeah, this is a W.
Oh, I see.
Here, no I, just a comma, sorry, for the inner product, comma. Okay. So what that means is that you now know how to do this. And remember how we said for the journey from initial conv nets to res nets to then conv next, how what you want to think about is the entire operation of like the block, right? And the block doesn't have to be as simple as just a convolution followed by a ReLU, right? You can have a convolution followed by a ReLU followed by an MLP. Like you can do other interesting things. The same spirit applies here, right? The aggregation operation is that entire block. You can think of that. So we now understand how to make the counterpart of the convolution. At this point, it's pretty much smooth sailing. You know, we've kind of overcome the major obstacle in a graph neural net in terms of conceptually what we need to do. Because now, can I have depth to increase the receptive field? Yes. I just copy the graph over and over and over again, right? I have this, it's had layer after layer after layer, which has potentially different operations that I'm running, right? Just as a convnet. And the same aggregation, so the aggregation that happened in a convnet happened because the channel information for a particular graph pixel depended on its neighbors in the previous layer. The same thing is true here. And so you get the same thing happens for free. Same architecture. Can I use residual connections to prevent dying gradients? Yes, for the same reason as I prevented dying gradients before. So as long as I structure some of these layers to be such that the channel information adds, I will get the same benefit that ResNets gave me before. Right? So I won't have dying gradients. Think about the normalized, yeah.
Well, when you're building a convnet, like you can change the filter size such that you can touch more of the neighbors. So, but in this case, like you're kind of fixed. Like how do you adjust?
Yeah, it's a great question. So the question was, in a convnet, you weren't limited to 3x3s. You could use 5x5s and 7x7s, usually odd numbers, right? Because me is in the center. Here, we kind of started off by saying, look, we only have information for you from your neighbors. The question is, how could you basically make something bigger? So you can, right? You can by, for example, taking two graph layers where you take information from your neighbors first, store them somewhere, right? And then do it again, right? And then look at your, alternatively, you take your 2-hop neighbors and you just include those, you pass information that includes those lists. There's nothing that says we have to make everything the same size. The only thing that makes us use vectors, so why do we use vectors in deep learning? We use vectors because we know how to think about linear algebra with vectors. That's one reason. And the other is that we have operations on our GPUs and CPUs that work well with vector matrix operations. In graph neural nets, the same underlying design considerations are true, except it turns out the reason you have these special libraries and the like is that getting stuff to map properly onto the GPU is not easy. Like it can be tricky to get it to work. And so people have thought about how you do that in a smart ways. Because if you did the nice thing about images is they're already arrays. Right? So they're already arrays and vectors. So it's much easier to work with. Here you have a general graph, and so you have to kind of work a little bit. But yes, you can basically aggregate information from 2-hop neighbors out, for example. People tend to just say, look, I'm going to count on the layers to do that. And I'll just make sure that I have sufficient richness to do that. OK, so next comes to normalizations. So if I think about normalizations, I'm going to talk about normalizations now in their own thing. So I want to keep that up. So let me, yeah, I'm fine. Normalizations. So let's start with the, are normalizations trivial or easy to do in the context of a graph neural net? And this fundamentally boils down to understanding what kinds of operations you can actually do or not do, practically. So let's start with the easiest normalization to think about from an implementation point of view. You all implemented batch norm, and batch norm was easy to think about conceptually, but you saw implementation-wise it was tricky, right? So let's think about the one that's easiest to think about from an implementation point of view, and that's layer norm. Let's think about layer norm. So remember, for layer norm, we had this picture. Let me just draw the picture. It's like the picture we used to talk about normalizations, where we had pixels, channels, and batch entries, right, for our 3 axes. And layer norm was a normalization that we said went like over a single entry of the batch, but it did everything across pixels and across channels as a normalization. Remember? That was layer norm. So this is for CNNs. So if I were to think about a graph, a GNN, see if this pen works, use a different color. Which of these do might be different? So what is the counterpart of pixels for a GNN? Nodes, right? Channels are still channels. And batch is still a batch, in principle. Okay, well, for now. So now the question is, can you do this normalization? And at first, the answer is yes. Go ahead, do it. But here I want to cause you to first realize there might be something different in practice in GNNs. So in a GNN, it kind of depends on how big this graph is, right? So when you think about images, your images are usually something which are, they're like, 100 by 100, or maybe they're 1,000 by 1,000, right? But even if you get, and practical images don't get too much bigger. They can, and if you get too much bigger, you end up with a problem that you can't actually keep all those pixels. So in traditional CNNs, what you do is you have early layers that quickly downsample you down to some smaller size for the image that you think of as being the kind of useful size. Now, if your graph is a giant thing, for the case of some operations, for some application contexts, your graph might be like Facebook's connectivity graph for all of its neighbors, for all the people and their connections. You can't do this. You can't practically do the averaging across the quote nodes, because there's too many of them. Does everyone see that? So this is the first place, again, when the normalizations, we see there might be a challenge. Actually, the instant you recognize that that could be a challenge, you realize that, oh, wait, it's kind of weird. How do I actually think about training when I can't actually hold the image in memory? Does everyone see this? So this is the first place where kind of in this list where you encounter this difficulty, but it's actually a serious difficulty. So what do? Well, you can do the easy thing, which is to say, maybe I'll only have a subset of nodes that I average over. You can also just imagine doing it kind of at the level of just myself, my one node. Right? I just normalize at this particular node. That's only really useful if you have lots of channels for it to be meaningful, right? Otherwise, you're really squishing it down too much, getting rid of too much information. But this is an implementation challenge. So any of the normalizations that goes across pixels in CNN has this challenge. So let's now talk about also batch norm. So in batch norm, what you did was you said, well, you use a different color. I have different colors here. Do they work? That's the question. Ah, yes. So batch norm said, look, we're just going to keep the channels separate from each other. We're not going to mix information across different channels. We are going to go across pixels, and we're just going to go across batches. So remember, the motivation for this is to think of each of these channels as being like a particular kind of feature that's being learned. So that's batch norm. Same problem. Right? Already in layer norm, we saw that if your graph is enormous, you can't even load the entire graph into memory. How are you ever going to load multiple copies of it? Right? Which is what batch norm would want you to do, to hold multiple images. So this is kind of dead, right, from this point of view, unless we kind of think about what do we actually mean with batches. So this is the important aside that we're trying to build towards here. Like that this normalizations is making us think about, forcing us to think about. Batches. Or mini batches, right? Mini. So if you think about the training of a graph neural net, what you need to do is you need to be able to see what happens as you suppose your task actually has labels that are interesting at the level of every individual node. You need to basically be able to look at only a subgraph at a time, okay? For large graphs. So need to sample, for practical reasons, a subgraph. Can't hold the entire graph. And this is where your go-to strategy fails. Your go-to strategy for sampling a subgraph would be, let me just randomly sample a set of nodes. Okay? But imagine if you did this on Facebook, right? So you have the Facebook graph that has everyone and their, who they're connected to. And you say, I can afford 1,000 people to hold in memory. So I'm going to sample from these billion people 1,000 people at random. Okay? If you did that, would there be any edges between them? Maybe, right? Like, probably not. You've lost all the local connectivity information. So naive approach doesn't work. All edges, basically. So all the neighborhood structure is destroyed. So you need to sample more intelligently. There's many, many papers on how you do this sampling. But the default kind of strategy is you first sample some nodes to sort of be the important me's, right? And then you sample their neighbors out to some extent out, right? So instead, sample targets and their neighbors. So usually what people do is they'll sample a target, they'll sample a certain larger fraction of their immediate neighbors, and then a smaller fraction of their immediate neighbors and a smaller fraction of their immediate neighbors to get some size of a local graph that you hope has information that you want. Any questions on this? This is the other thing that's different in graph neural nets from conv nets. And it's induced by the fact that you have size. Yeah?
Can we do some kind of clustering before we apply the graph?
Yeah, great question. The question is, can you apply some kind of clustering on large graphs? And the answer is yes. People can try to do that, try to apply some kind of clustering on the large graph. It's a little tricky, though. The thing that's a little tricky is, suppose I gave you a cluster. I said, here's my graph, and it's my larger graph, and it actually has these 10 clusters in it. So now, what are you going to do? Are you only going to sample, are you going to sample an entire cluster at a time, or subsample the cluster? Or are you going to sample across the different clusters in your batch? You can see how there's could be logical reasons why you'd want to sample across the different clusters to get diversity, because these clusters might actually be different from each other, and you want to make sure the weights you're learning are good. So it's not an obvious, you still have to deal with this subsampling of the graph problem, typically. That's a good question, though. So anyway, so you have this issue with how to deal with batches, which is important and practically significant. It's something where the examples we're going to give you, in like coding, is like you won't have to deal with it. It's all small, everything will fit in memory. But it is important to understand. Okay, so with that point made, you can imagine counterparts of batch norm as well. And so people have normalizations that they use. Yeah?
Question, are the samples the same size, or we need to do the same size, or is that random?
It's a great question. The question is, if I'm doing a mini batch sampling, do I always sample the same number of nodes at the end of the day? The answer is you'll try to. Because probably you're limited by, all the same basic considerations apply. Like what's limiting your batch size? What's limiting your batch size? It has to fit appropriately in GPU memory. And so there's lots of optimizations one can do to do this. So it's not always the same size, because sometimes what you want to do is to make it that it depends on what your graph looks like. Right? So you want to make it that as you run iterations, as you run your graph neural net through different layers, you're going to have information coming from different neighbors. And if your batch size is such that all the neighbors you want can fit into GPU memory, great. But sometimes you're going to be like, I can actually have some stuff in CPU memory and swap it in and out. I'll pay the memory transfer cost of moving stuff from the CPU memory to the GPU memory. And so you'll try to balance the right optimum performance of you want the batch to be the most effective. And so you might have different sizes. But the default is, pick the same number of things so it all fits in memory. Great question, actually. And people have written many papers on this topic of how do you optimize this in real-life systems. Again, remember, these GNNs are incredibly practically important. They're not like paint me a dog. This generates money for companies. So they have large teams invested in making this stuff work well. Okay, so basically, we can kind of do the normalization stuff for large graphs. For smaller graphs that fit in memory, everything just kind of carries over. Final comment of thing that's left is pooling to downsample. And speed up the growth of the receptive fields. And this is where, in a way, you're kind of stuck for a graph. Because what you would want is a way to subsample to thin out a graph. Right? You'd want to thin out a graph. Now, in different domains, this is very domain-specific. The answer is domain-specific. If your domain is something where there's already a well-established way to think about how you would thin out a graph, then you can imagine doing pooling by doing graph thinning appropriately. But that's also, you can think of as a way of kind of doing clustering. of some kind. So you cluster a bunch of related nodes together. You say this is now one big node. There's a group of related nodes. Let's cluster them together to one big node. But that's always something domain specific. In a way, pooling to downsample for images is also domain specific, but there's only exactly one domain, image. And so it's easy. But here, it really does matter. And so in many graph neural network settings, people don't do a counterpart of pooling along the way to make your network go from big things to smaller things for further processing. You typically just keep it processing throughout on the entire graph. You might do at the end something like a global average pool or things like this before you do the final classification, if it's graph level classification. But pooling is very domain specific. Okay, in the 5 minutes I have left, I wanted to talk about the other thing. So everything I've been doing. So okay, I'm going to take all these specific simplifications we did and like back them out, okay? So I've already backed out the edge labels. If you have edge labels, add them in, okay? There are alternative things where you can actually have separate edge representations and have messages being passed through edges. But the easiest case is just add the edge labels in. We've talked about everything still with the idea that we have a single graph topology and all of our data set consists of just different labels. So now I want to remove that. Suppose I'm talking about molecules, right? I'm talking about a graph level task, and my different molecules have different graphs. I want to eliminate that, this assumption. Does everyone see the question we're trying to do? Now for images, we had the images are all starting off and they're all certain size, right? And that's why we went for this. So whenever you want to remove an assumption, you should first check whether the easiest way of removing the assumption works. What's the easiest way of removing an assumption? You ignore the assumption, and you see if you get a seg fault or something breaks. Right? Does it stop compiling? Do you see what I'm saying? Does everyone understand this approach? It's the let's hope it works approach. So let's just eliminate this assumption. Okay? And see what happens. Okay? So now, it turns out that nothing breaks. Okay? And the reason nothing breaks is that the local neighborhoods of our graph already had a diversity of neighborhoods in them. So even for one graph, different nodes had different neighborhood structures. And you had to deal with it. And the algorithm is the approach we're taking is fundamentally local. You just pass you look at information coming from your neighbors, process, add channels, and that's your new graph. So you're still going to have the same graph you started with throughout. But everywhere locally, you never counted on the whole thing being the same. You just count on the fact that my neighbors are the same at the next time step. And that's always true. I mean, in this context, right? The graph isn't changing during the processing of the graph neural net itself. And so we just drop, this assumption is only there for thinking, and you can remove it, and everything still works. Most treatments of graph neural nets don't start with this like scaffolding assumption, and sometimes students get confused about that. So I started with the scaffolding assumption, even though it's completely unnecessary, to help kind of make it clearer what's going on in terms of the analogy to CNNs. Now, the final assumption that I want to deal with in my 1 minute is actually the assumption that we have a graph level task. So if your task isn't graph level, but is instead at the node level, and you just have one graph, we have a very basic problem, which is, what do we even mean by a train test split? Okay? So if you have a graph and you have so these are node level problems. So for node level problems, if you have only one graph, which is like we gave you on the homework, then you still have to think about what does it even mean to have a train test split? Like even the most basic thing you have to worry about. Because if you only have one graph, the train test split you're going to have is necessarily going to require you to look at a subset of the graph in terms of labels. So what you're going to do is you're going to hold some parts of the graph back. And for holding out parts of the graph, it turns out you have two choices of what to do. One choice is the easiest choice to think about, and the one you should always try to do if it works, is just delete that part of the graph from the perspective of training. Right? The part that you're holding back, just delete it. Remove it entirely. Then you have no problem. You're training on your graph, on only the training data parts, and then you test on that part of the graph put back in. Okay, does everyone see that? That's like an easy way of doing it. Sometimes, though, that performance of that will be particularly bad, because by removing the held out parts, you're destroying the connectivity structure of the graph. There's information that should be flowing that isn't going to be able to flow. And so sometimes what people will do is they will have those nodes in, except remove their information. Like they'll be in the graph, but they will have like only dummy information for their vectors associated with them. Right? And you say that way they can still participate in terms of connectivity, but they can't, there's no cheating going on where they're learning something that, Does everyone see the issue? The kind of thing, basically, hold them. If you want to hold some people back from a social network, you can put them in as dummy generic people or with randomized data. So after that, basically, you should be able to figure everything else out yourself for a graph neural net. So sorry I've gone a couple minutes over, but with this, you should be set for the homework. Next time, we'll maybe finish up a few more comments on graph neural nets, and then we'll move on to RNNs.